Hello, I welcome you all to this another interesting screencast. The problem reads determine the minimum force P to prevent the 30 kg rod AB from sliding. The contact surface at B is smooth, whereas the coefficient of static friction between the rod and the wall at A is mu s equal to 0.2. So I'll modify this here. I'll say minimum and maximum. Okay. So I want us to calculate two values there, minimum and maximum, to prevent the rod. All right, to prevent the rod from sliding. And then we've been told the contact surface at B is smooth. All right. So the reason I indicated maximum there is a concept I want to just again emphasize. So every time we are dealing with, of course, dry friction, whose maximum is equal to mu s, just rather mu times n, where mu can either be s for static, k for kinetic. Okay, so we know what friction is. This is a force that resists the movement of two contacting surfaces that slide relative to each other. So there are three types of dry friction problem. Okay, three types of dry friction problems. All right, the first one is where you are experiencing no impending motion at the contact surfaces, at the contact points or contact surfaces. Okay, no impending motion. All right, so for this particular case, we expect the number of unknowns to be less than or equal to the number of equations of equilibrium. Okay, so in this particular case, we are saying there is not going to be any impending motion, and we are able to solve the problem directly by using the available equations of equilibrium. And after we've done so, then we need to check for slip. Okay, and if this equation is obeyed, then we expect no slip. All right, the second one is where we are saying there is impending motion at some contact points or surfaces. So there is some impending motion. In this particular case, the number of unknowns is greater than the available equations of equilibrium. Okay, in this particular case, we also use so we need to also use the friction equation, which is F equal to mu times N. Okay, and okay, I'll talk about that later on. And in the third case, this is where we have impending motion. We have impending motion at all contact points. This is where we have motion at all contact points, okay, stroke surfaces. And in this particular case, these conditions also apply. All right, these conditions apply. These ones, they do apply. The number of unknowns are greater than the number of the equations of equilibrium, and therefore we need to use F equal to mu N. For these two cases, the second and the third. When we are writing our free body diagram, F must have the correct direction. Okay. Here we don't have room to assume. All right. Here we need, when we are indicating the direction of our friction force, it must be in the right direction. Okay. Here, the first one, we can assume the direction of F. Even when we assume the wrong one, we are going to get a negative value to correct that particular direction. Second and third case, we don't have that luxury of assuming. We need to have the right direction. Okay, it's really very important. We are going to see in this particular problem what happens when we change the direction of our friction force. Because I've indicated deliberately there, I want us to calculate the minimum as well as the maximum value of P. That will prevent the rod from sliding. Okay, so let's do that. First things first, let's draw the free body diagram. So at 8B, there is no friction. We've been told it's smooth. Okay, there is no friction. Okay, remember this. We are told this point here. At the contact point at B is smooth. Okay, it is smooth. And then let's draw the free body diagram. So we only expect a normal force there, like so. And then here we also expect a normal force like so. And then we have the weight at the mid span there like so. What else? So the first case, let's work out the minimum. All right. So this rod, let's look at this rod. So for us to get the minimum, what do you think the direction of our friction is supposed to be? So for us to get the minimum, we are assuming this rod tends to move against the wall in this direction. Okay, or this will allow us to calculate the minimum force there. Okay, the minimum value of P. So this is the direction that we are assuming this rod tends to move. If it was to move there, therefore friction will be going where? Up. Okay, so our friction here will be going up like so. Okay, let's label this very quickly. So here we expect normal force NB, and there we expect normal force NA, then we have the friction force F, then this is W. Okay, and then this length, let's just work out this length. This length is just going to be equal to, let me work out this length. All right, like so. Okay, there we go. Okay, so this one here, this length here, we're going to use Pythagoras. It's just 4 squared plus 3 squared. Square root of that, this gives us a 25, which is equal to 5. So this is 5. Therefore, this will be 2.5. This length will be 2.5, and so is this. These are all meters. Okay. And then we have the slope, of course. We already know the slope. We are just using to define this, we're just going to use the right angle triangle to define our slope, which is just that. So we'll have this value here, which is a 4, and here we have 3, then there we have a 5. Great. So let's count the number of unknowns. So the number of unknowns are equal to, how many are they? We have NB, we have P, we have NA, and F. There are 4. Okay, so that is NA, NB, P, and F. Okay, then the number of the equations of equilibrium, there are how many? 3. And since the unknowns are more than the available equations of equilibrium, we will need to use the friction equation. F is equal to mu n. So the moment we use this particular equation, like I said earlier on, the direction that we place or the direction that we use in our free body diagram has to be the correct one. All right. As you are going to see, we are going to work out this, find the minimum. We are also going to assume that the friction is the other way around. We are going to realize that to find another value. Okay. So we are assuming that at A, there is going to be some impending motion. So this case is, we are saying this is case number 2, where we are assuming impending, this is impending motion at A. Okay, so let's find the minimum. So let's say case 1, we want to find the minimum. Okay, so minimum value of P. All right, so this is the first case. So what do we do? Of course, let's work out the values of the values that we have. So we have W there. W is just equal to 30 by 9.81, and this gives us that's 30 by 9.81. This one is just going to be equal to 294.3 newtons. So 30 by 9.81 is 294.3 newtons. So let's start. So like we said, this is going to be equal to this is the friction force. Okay, we already have that equation. Let's sum up all the forces. So sum up forces in the x, in the y, and we'll take moments. So let's say summation of forces in the x direction equal to 0, in this direction being our reference. What do we have? We have P minus NA, okay, equal to 0. And therefore, our P is just going to be equal to NA, right? And then we have summation of forces in the y equal to 0, going up being our reference. So we have NB minus W plus F equal to 0. Okay. And then we have summation of moments about point B equal to 0. Okay. And clockwise being our reference. So we have this, we have minus W by 2.5 by the run. So let me just close up this. So 2.5 by the run, which is a 4 divided by 5. Okay, and then we have plus F by 4. Then we have plus NA by NA by 3 equal to 0. Okay, we do have another equation which is equal to friction equation because the unknowns are more than the available equations of equilibrium, so we are forced to invoke one friction equation at A, F equal to mu by the normal force, and this is equal to, what is the coefficient of friction given? Been given is 0.2, so this is 0.2 by NA. So what we'll do now is we are going to replace this F, we'll replace it here, okay, and then W, we already know it, we just need to go and collect it there. So this is W, so replace there W, and once we do so, we can directly calculate the value of N. Okay, you make NA subject to the formula, which you can do. If you can't do it directly, you can always write it down. You don't have to follow what I'm doing. 294.3 minus by 0.2. Again, the slope here, it was not very necessary because we know this is just going to be equal to 2 there and also 2 there. Okay, but no big deal. All right, it still give us the same values. Okay, great. NA is equal to minus 294.3 by 2. That 2.5 by 4 over this one here gives us a 2. This one there, the slope gives us a 2. So 294.3 by 2. Okay, then we have divided by, we replace that becomes 0.2 by 4 plus 3. Alright, so we'll have NA equal to 154.89 newtons. And we know that our P is equal to NA, remember this here, okay? Therefore, P minimum is going to be equal to 154.89 newtons. Alright, like we said in our problem, we also included one part which was not part of the problem to just appreciate this particular problem. So we said, let's also find the maximum value of P that we can apply to prevent the rod. We can apply without making the rod slide, okay, at A. So let's go to case number 2. I will call it case 2. Case 2. And case 2 is max value of P. Okay. So we want to find the maximum value of P, which will still make this particular rod not to slide at A. So in this case, we are assuming that our rod, let me use blue, we are assuming that our rod here, instead of going up, because we want to find the maximum, it tends to slide up like so, okay? This is, so instead we are going to change the direction of our F, okay? Does it make sense? Remember what we did initially? So change the direction of our F. So instead of facing down like so, because we want to find the maximum, this is how important it is. Like I said, remember we said when we have the case where we have impending motion, we always need to assume the right direction. Okay, so there we go. So this one we are calling it F. Okay, so let's find this value. So in this case, the equations are the same. W is the same. It's the same W here, which is nothing changes. It's 294.3 newtons. Then we have summation of forces in the x direction. It still remains the same, which is just a P minus NA equal to 0. and then we have summation of forces in the y. Nothing changes. Of course, we don't even need this. I'm just including it. Okay, NB minus W minus minus F equal to 0. Okay, so here we have two minuses. Of course, the useful one is the summation of moments about point B. Again, if you want to, you can take moments about point A. Me, I took it about point B. So we'll have minus W by 2.5, which is just a 2. Okay, divided, by 4 over 5. Then here we'll have a minus F by 4. Then we'll have there a plus NA by 3 equal to 0. Alright, so we replace the values and then we also have the friction force, because we have more unknowns than the available equations of equilibrium, which is 0.2 NA. So now we feed everything in our equation. We'll find that the value of NA is going to give us, let's do the calculation. So we'll have 294.3 by 2, and divided by, we have minus 0.2 by 4 plus 3. Okay, right? 0.2 by 4 plus 3. Okay, so this gives us a 267.55 newtons. Let me check it again. That's 294.3 by 2. Okay, and divided by, we have a minus 0.2 by 4 plus 3. Okay, alright, 267.55. Since we know here that our P is equal to NA, therefore P max, this is P max, therefore P max is going to be equal to 267.55 newtons. So again, this is the maximum force that we can apply at P without causing this rod to slide. So we have the minimum, okay? We have the minimum that we can apply, and then we have the maximum, okay? Right, so let's now just outline the solutions. So the minimum is what we have been asked, which we calculated, but I decided to also add one part with the maximum. Okay. One catchword, there is impending motion at what? At A. So impending motion means the bar at A is at the verge of moving. So if we slightly increased our maximum force, if we increased P to even at 0.1, then we expect motion at A. Alright, so we have a range of values of P from 154.89 to 267.5. This is the range of values, okay? We can play around within this particular range without the rod moving at A, okay? This is our range, P minimum and P maximum. We cannot go beyond P max, okay? We cannot go beyond P max, right? Okay, and then we can also not reduce our load, okay, below P minimum. So we cannot go below P minimum, we cannot go beyond P max, right? We cannot go below, so we cannot go below P minimum, okay, and we cannot go beyond P max. Okay, we cannot go below P minimum, we cannot go beyond P max. Okay, for us to allow this particular rod to remain in that position without sliding. All right. I hope this video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye. See you in my next screencast.